Okay, Vamdev, shall we continue?
Sir.
Why Anaga also did not come?
Sir, message, sir.
Huh?
Sir, I'll put her a message, sir.
Yeah, I tried to call her, but she did not live. You're able to see the board now? Vamdev?
Yes, sir. Yes, sir.
Okay. So yesterday we have seen the factors influencing the acceleration due to gravity, correct?
Yes, sir.
Yeah, in that last point you can add one more, that is you can add it, lines drawn on the globe. You can put note and write. Lines drawn on the globe joining. Lines drawn on the globe joining the places with equal values of lines drawn on the globe joining the places with equal values of acceleration due to gravity. Equal values of acceleration due to gravity are called isogons. Are called isogons. Are called isogons. Okay, we'll continue after that. What is the number, Vamdev? Fifth one,
Sir,
huh?
sir. Roman numeral 5, sir.
Okay. Correct, huh?
Sir, Roman numeral 5, sir, we completed last class, sir.
The factors are over. What is the next serial number?
6, sir. Roman numeral 6.
Not Romans, Arabic.
Okay, sir.
Factors affecting G, 5, huh?
Yes, sir. Oh, yes, sir. Yes, sir. Yes, sir.
Okay. Now, sixth one is escape velocity.
Sir, Anagha is saying she'll join, sir, in 1 second.
Okay, okay. So this is the Earth's surface.
Good evening, sir.
Yeah, good evening, ma'am. So it is Earth of mass m, radius r, density rho. It is a body, so it should be given enough velocity so that it never returns back to Earth. That velocity is called as escape velocity. The velocity with which a body should be projected so that it escapes out of Earth's gravitational pull is called the escape velocity. Voyager 1, Voyager 2, which already crossed our solar system, they should be projected with escape velocity. Please write the definition. The velocity that should be given to a body, the velocity that should be given to a body with which it escapes out of, with which it escapes out of the Earth's gravity, with which it escapes out of the Earth's gravity. Comma is called the escape velocity. Is called the escape velocity. So the concept here is the needed kinetic energy to escape is equal to work done on the body against the Earth's gravitational pull. So K is equal to W is equal to integral f dx, because here x is changing from Earth's surface to infinity, where f is equal to fg is equal to g capital M small m by x square, because x is varying. So we get this as g capital M small m. They're all constants. Integral dx by x square, x1 is equal to r, to x2 is equal to infinity. That is g capital M small m integral x to the power of minus 2 dx, same limits, x1 is equal to r, to x2 is equal to infinity. So there is a formula for integration, Anaga, I think you may be knowing it. X to the power of n dx is equal to x to the power of n plus 1 by n plus 1.
Yes, sir. Yes, sir.
So according to that, this will be g capital M small m x to the power of minus 2 plus 1 by minus 2 plus 1, x1 is equal to r, to x2 is equal to infinity. So this will be g capital M small m into 1 by x minus 1 by x minus 1 by r minus 1 by infinity. So 1 by infinity is 0. Minus of minus will become plus. Therefore, it becomes G capital M small m by R. So half m V square, kinetic energy with which it escapes, is equal to G capital M small m by R. So if you cancel m on both sides, then we'll get V square is equal to 2gm by R, implies the escape velocity is given by root of 2gm by R. So if you substitute all the values for F, I'll do it. Please copy it. So this integration formula we have to use whenever it is the any variable parameter is to be added.
Sir, so would the escape velocity for any body irrespective of its mass be same, sir?
Yes, whether it is for ant or for elephant, the escape velocity is independent of the mass of the body to be projected. That I am going to tell you. V varies directly as root m by r. M is the mass of the planet, r is the radius. So V varies directly as root m by r. Completed, eh?
Yes, sir. Yes, sir.
Kamdev, అయిపోయిందా?
Yes, sir.
Yeah, you can write there. That is escape velocity of a body. That is escape velocity of a body is independent of its mass. Escape velocity of a body is independent of its mass. Is independent of its mass. That is, it will be same for both ant and elephant. That is, it will be same for both ant and elephant. Then, third one in this, you know, small g is equal to gm by r square. So, capital G is equal to gr square by m. So, VE can be written as 2m by r into gr square by m. So m is cancelled, one r is cancelled. Implies V is equal to root of 2gr. So g is the acceleration due to gravity on the planet. So V is equal to root 2gr. And you know, acceleration due to gravity, we wrote it as 4 by 3 pi g rho r. So if you substitute in this, we'll get the formula for escape velocity in terms of density. So it is root of 2r in place of g, 4 by 3 pi g rho r. So this 4r square can be taken out. Hence it is 2r under root of 2 by 3 by 0. Rho stands for density of the planet. So if you substitute the values, V is equal to root of 2gm by r, value of VE from the earth. So this will be root of 2 into 6.67 into 10 to the power of minus 11. Mass of the earth 6 into 10 to the power of 24 by earth's radius 6.4 into 10 to the power of 6. So this is 11 plus 6, 17. You are left with 10 to the power of 7. So 110 can be taken out, and if you simplify, this will be coming out to be 11.2 into 10 to the power of 3 meters second inverse, or 11.2 kilometers per second. This is from the Earth's surface. Okay, na?
Yes, sir. Yes, sir.
Gandhi, అయిపోయిందా?
Yes, sir.
Okay. Then next is orbital velocity. Represented by V naught. So here is the Earth. This is the axis, and here is the orbit at a height h, and this is the Earth's radius. Now a satellite is to be launched so that it has to move around the Earth with a specific velocity, falling under the influence of Earth's gravity. So that is called as the orbital velocity, the minimum velocity that should be given to a body with which it revolves around the Earth in a specific orbit. That is called as the orbital velocity. Please write the definition. The velocity that should be given to a body the velocity that should be given to a body with which the velocity that should be given to a body with which it revolves around the Earth, with which it revolves around the Earth in an orbit, is called the orbital velocity. Concept is the required centripetal force on the satellite will be equal to the Earth's gravitational force. So centripetal force formula is mv square by r, that is mv naught square by r. V naught is the orbital velocity. Earth's gravitational force is g capital M small m by r square. So this derivation is easier. This implies V naught is equal to root of g m by r. Using the relations, we can get it as root gr is equal to, it is, hey, so it will be 2r into root of 1 by 3 pi g rho. So if you substitute the values, we will get V naught is equal to root of 6.67 into 10 to the power of minus 11 into 6 into 10 to the power of 24 by 6.4 into 10 to the power of 6. This will be coming nearly 7.99 something, 8.8 into 10 to the power of 3 meters second inverse, or 8 kilometers per second. Next, we got VE is equal to square root of 2 gm by r. This is root 2 into root gm by r, implies VE is equal to root 2 V naught. Yes, VBC पर टच कर रहा है. Yes, VBC. Therefore, the percentage increase in the velocity of orbiting body for escaping it is delta V by V naught into 100. That is VE minus V naught by V naught into 100. V into 1.414 minus 1 into V naught by V naught into 100. So if you can increase the velocity of orbiting body by 41.4%, then it escapes into the space. Next, if the height of the orbit is comparable, then we get V naught will be equal to root of gm by r plus h. Even V naught depends directly on the mass of the Earth and inversely on radius, but not on the mass of the orbiting body. That's why You can dump any amount of payload into the space. Hence, no limitations for the payload to be sent into the space, because the orbital velocity is independent of the mass of the body to be projected. Aina?
Yes, sir. Yes, sir.
Kamde ayipinda?
Done, sir. Done, sir.
One more is there in this. Time period of revolution. We got orbital velocity is equal to root of root gr. This is equal to v is equal to r omega relation. Omega naught is the angular orbital velocity. So from this we get omega naught is equal to root gr by r. Let us take this r also into the square root. So root gr by r square. Therefore, angular orbital velocity comes out to be root g by r. And we know t is equal to 2 pi by omega naught. Therefore, the time period of revolution of satellite is given by 2 pi root of r by g. So let us substitute the values. 2 pi into 6.4 into 10 to the power of 6 by 9.8. So 2 pi into 10 to the power of 3 into root 64 by 98. So 2 pi into 10 to the power of 3 into 8 by 7 root 2. 98 is 49 into 2, that is 7 root 2. So if you simplify this, we'll be getting 84.6 into 60 seconds or 84.6 minutes. So if the time period of a satellite which orbits very close to Earth's surface is 84.6 minutes. Here height of the orbit h is very much less than Earth's radius. Second, if height of the orbit is greater than or equal to r, comparable to r, then v naught is equal to root of gm by r plus h is equal to, yes, in place of r omega, it is r plus h into omega naught. So using that, we will get omega naught is equal to, yes, it will be root of gm by r plus h whole cube, because if it goes into square root, it will be squared. This will be, of course, equals to 2 pi by capital T. Hence, the time period of a satellite whose height is comparable to Earth's radius is given by 2 pi under root of r plus h whole cube by gm. If H is very much less than R, then T is equal to 2 pi root of R cube by Gm, implies T square is directly proportional to R cube. This is nothing but Kepler's third law. Correct? Huh?
Yes, sir.
Yes. And we have a satellite called geostationary satellite. It is normally used for communication purposes. Televisions, telephones, everything, all communication devices will work only with the help of geostationary satellite. For a satellite to be geostationary, the orbit should be in the equatorial plane. So you cannot project geostationary satellites everywhere from the globe. You have to project only from the equatorial plane. Our India has got the greatest advantage of having Sriharikota, which is the best launching pad with longest ocean range and is lying in the equatorial plane. Next. Direction. So it should be directed in the direction of Earth's rotation, that is from west to east, so that the relative velocity of satellite with respect to Earth will be 0. Means always the satellite appears to be parked there. Next time period should be same as that of Earth's rotation. So if you substitute T is equal 24 hours into 3600 seconds and R GM values and get the value of H. So the height of geostationary satellite, not only geostationary, any satellite can be found using that formula. So you square it on both sides. It will be Gm by GMT square by 4 pi square will be equal to R plus H whole cube. So take the cube root. R plus H will be GMT square by 4 pi square to the power of 1 by 3. Therefore, the height of the geostationary orbit is given by GMT square by 4 pi square to the power of 1 by 3 minus R. This will come out to be almost 6 times the Earth's radius. So the geostationary satellites, all these INSAT satellites, etc., they will be at a height of 6 times the Earth's radius, means around 38,000 kilometers altitude. Understand? So
Yes,
this
sir.
is about the geostationary satellite. Copied?
Yes, sir. Done,
Yes,
sir.
sir. Yes, sir.
Good. Now the last one in this is energy of satellite. Every satellite in its orbit is moving with some velocity and its configuration is stable with respect to the Earth. So because of its stable configuration, means the satellite is not falling onto the Earth's surface. It is always remaining at that altitude. So because of the stable configuration of the satellite in the orbit, it possesses potential energy. Since it is moving with a speed v, it will have the kinetic energy. Therefore, the total energy of the satellite is U plus K here. So potential energy of the satellite. It is nothing but work done in shifting it from Earth's surface, say 0, let us put 0, to the very nearby altitude. This is integral f dx. X1 is equal to 0 to x2 is equal to r. Here we are assuming that the height of the orbit is negligible when compared with Earth's radius. All the remote sensing satellites will be very close to Earth's surface. Even the International Space Station, its height is very small, few kilometers. So this is integral g capital M small m by x square into dx. So we'll get this formula for potential energy as g capital M small m by r. Next, orbital velocity of the satellite is root gm by r, and kinetic energy, of course, is half mv naught square. Therefore, I get g capital M small m by 2r. So total energy of the satellite is minus g capital M small m by r plus g capital M small m by 2r. So it will be minus g capital M small m by 2r will be the formula for total energy.
Sir, but sir, how can energy be negative, sir? Because it is scalar.
Negative sign means it has got a physical significance. It does not like, it's not like your vector negative, positive, negative vectors. The negative sign means here is the Earth and here is the satellite. So satellite is always constantly pulled by Earth's gravity, but it is held in the orbit against the gravity. Yes or no?
Yes, sir.
So the
Yes, sir.
negative sign means that the satellite has got a stable configuration in the orbit against the Earth's gravitational force. That's the meaning of it. Understood?
Yes, sir.
Yeah. And here, if the height of the orbit is considerable or comparable to the Earth's radius, then potential energy will become g capital M small m by r plus h. Kinetic energy will become g capital M small m by 2 into r plus h, and the total energy will become g capital M small m by 2 into r plus h. This is for the orbit whose altitude is comparable to the Earth's radius. Okay.
Yes, sir. Yes, sir.
And the last part in this is universe without gravity. First of all, if you read the birth of a star, the basic parameter for the birth of a star is the self-gravity in hydrogen and helium gas clouds. So the self-gravitational force will start contracting the hydrogen and helium gas clouds, and once the contraction crosses the limits, the collisions of atoms begin, increasing the interior temperature from minus 173 degrees centigrade to 10 million degrees centigrade. So at this temperature, the star begins to generate energy, and once the energy generation begins, further contraction stops because of the equilibrium between self-gravity and the forces arising out of energy produced. So the very reason for the birth of a star is the gravitational force. Next, orbital motion of planets. Around star, that is sun, and satellites around planets, that is also because of gravity. Then tides on the earth are because of gravity. Atmosphere is held because of gravity. So if gravity is not there, number one, star cannot born. Second, no planets will be revolving around their parental stars. No satellites will be moving around the planets. No tides are there. No atmosphere will be there. Hence, life will not exist at all. Therefore, we cannot imagine the system to survive for millions and trillions of years if the gravity is absent. So gravity is must for the universe to sustain. Yes or no?
Yes,
Yes,
sir. Yes, sir.
Have you noted, Alma?
yes, sir.
Yes, sir. Yes, sir.
Okay. Yeah, take one problem. Two planets. Two planets have their masses in the ratio 6:8, and the radii in the ratio 4:5. Find the ratio of number one, accelerations due to gravity. Second, ratio of escape and orbital velocities. Ratio of escape and orbital velocities. Third, energies of satellites of same mass. So for this, I'll be giving you few concepts. Let us start with G is equal to Gm by R square. And even I gave you 4/3 pi G rho R, correct? Yes or no?
Yes, sir. Yes, sir.
So here, G varies M by R square. G varies directly as rho R. That capital G is constant, 4 by 3 pi g are constants. So from this I can write G1 by G2 is equal to M1 by M2 into R2 by R1 whole square. Antara? Correct?
Yes, sir.
Yes, sir. Yes.
Coming to this, sometimes you'll be given densities ratio. So rho 1 by rho 2 into R1 by R2. Suppose two planets are having equal masses. Then G varies directly as 1 by R square. So G1 by G2 is R2 by R1 whole square. Next, for the same density, G1 by G2 is equal to rho 1 by rho 2 since G varies directly as R. Correct? Ona?
Yes, sir. Yes, sir. Yes.
Yeah. So, can you do the ratio of accelerations due to gravity? You should use this formula. Because you are given masses and radii ratio, you have to use the first formula, correct?
Yes, sir.
Then, escape or orbital velocity varies directly as m by r, varies directly as root gr, varies directly as r root rho. చూడండి ఫార్ములా చూడండి. This is escape velocity, correct? VE
Yes, sir.
varies directly as m by r. VE varies directly as root gr. VE varies directly as r root rho. Yes or no?
Yes, sir.
Yes, sir.
You please add it there. Add it near those formulae. VE varies directly as root m by r. VE varies directly as root gr. VE varies directly as r root rho. This is for escape velocity. Next, coming to orbital velocity. See, V naught varies directly as m by r. V naught varies directly as root gr. And V naught varies directly as r into root rho. Avuna?
Yes, sir. Yes,
Yes.
sir.
Mamdev.
Yes, sir.
So, I can now write, that's what I write, VE or V naught varies directly as m by r, varies directly as root gr, varies directly as r root rho. So V1 by V2 is root of M1 by M2 into R2 by R1. Avuna kada?
Yes, sir. Yes.
R is in the
Yes.
denominator. Tarvata V1 by V2 is equal to root G1 by G2 into R1 by R2. Using this relation, V1 by V2, R1 by R2 into root of rho 1 by rho 2. Avuna? Sometimes he says two planets have same mass. Then V1 by V2 is root of R2 by R1. Two planets with same acceleration due to gravity. V1 by V2 is root of R1 by R2. Same density V1 by V2 is R1 by R2. So you can use this formula for ratio of escape and orbital velocities. Means VE1 by VE2 is equal to V01 by V02. Antena kada?
Yes, sir.
Have you noted it?
Yes, sir.
Okay. Anaka aindama?
Yes, sir. I pen, sir. Yes, sir.
Alage energy is equal to G minus G capital M small m by 2R. Tarvata potential energy minus G capital M small m by R. Kinetic energy G capital M small m by 2R. So whatever it may be, E varies directly as 1 by R, U varies directly as 1 by R, K varies directly as 1 by R. Ona?
Yes, sir. Yes, sir.
For two different planets, if he says U varies directly or K varies directly or E varies directly as M by R. Therefore, E1 by E2 is equal to U1 by U2 is equal to K1 by K2 is equal to M1 by M2 into R2 by R1. Okay, na?
Yes, sir.
Yes, sir. Yes,
Now
sir.
can you try that problem with these ratios?
Yes, sir. Yes,
Not
sir.
only that, you can create different ratios using these relations. Yes or no? You can take the densities of different planets and get the ratio of G, get the ratio of escape or orbital velocities, get the ratio of energies. Everything can be done based on this. Okay.
Yes, sir.
Tomorrow we'll do some more models of problems. Okay.
Yes, sir. Yes, sir.
Based on gravitation.
Yes, sir. Yes, sir.
Yeah. So when till how long you can attend the classes from there?
Sir, tomorrow last day, sir.
Tomorrow last day. Okay. Because we have to plan to Anaka. Okay.
Yes, sir.
Yes, sir. Yes.
Topics to be done for Anaka, I will be planning. So tomorrow we'll do problems on gravitation. Right?
Yes, sir. Yes, sir.
Yes, sir. Yes,
And
sir.
what about electromagnetic effects are left for you in
Sir,
your
can we do
ICSE
that?
syllabus? Huh?
Sir, can we do that after the board, sir?
Yeah, as per your wish. I am not you. I am thinking about you only. If you feel that it can be done after your exams, we will do it. No issue for me.
Yes, sir. Yes, sir.
So tomorrow we'll do these problems, and that leftover topic in your ICSE syllabus we'll be doing after
Board, sir.
your board exam. Yeah, before your physics exam, if you have any doubt, you call me. I'll try to explain you.
Yes, sir. Thank you, sir.
Okay, you can take my help before your board exam, right?
Yes, sir. Yes,
Yeah,
sir.
just call me afternoon, anytime after 2 o'clock. I will be free.
Yes, sir. Thank you, sir.
Oh, okay, right, Anaka. Tomorrow we'll meet.
Yes, sir. Yes, sir.
We'll complete problems from gravitation tomorrow. I'm there.
Yes, sir.
So bye.
Thank you, sir. Thank you, sir.
Okay.
Yes, sir. Thank you, sir.
Right.